Good morning, everybody. We're going to get started here. We're going to run a tight, hopefully a little less than 60 minutes today. So welcome to Star Trek. I hope everybody enjoyed their first session of the day. Over the next hour here, we're going to talk about our system at GetThru that sends a lot of messages to send messages. And we're going to see how many times I can say messages in different contexts, and hopefully I don't confuse myself. My name is Brian Meeker. I spent most of my career in C#, but these days I'm an Elixir dev at GetThru. I've worked 100% remote since 2012 in Indiana, so I enjoy getting out of my house and seeing people sometimes. You can find me mostly these days on Mastodon, and these slides will be available on GitHub after the talk. On the last slide, there'll be a link to the QR code, and I'll make sure they end up in the Star Trek GitHub repo as well. This isn't a sales talk, but I work for GetThru, and this talk is about a system we built, so I need to tell you a little bit about what we do. GetThru provides texting and calling tools for progressive political campaigns, nonprofits, and universities. And as you might have noticed, it's a presidential election year, which means a lot more usage of our system this year, and that led us to reevaluate our infrastructure to handle that load. We have two main products. ThruTalk is for phone banking. An education customer might use it to ask for donations during a university's giving day. A political campaign might use it as part of their Get Out the Vote campaign. For today, though, we're only going to be looking at ThruText. This is our main product. Those same kinds of use cases are possible with texting, and you're much more likely to get through, pun intended, to somebody. People don't want to answer phone calls from random numbers, but they will at least glance at a text message and maybe get annoyed at it. But let's look at our old system to understand why we needed to build something new. GetThru's code base dates back to 2016. Elixir went 1.0 in 2014, and that means we probably have one of the oldest continually developed Elixir code bases in existence. And like any system under development for a long time, core parts of our infrastructure have become creakier, people have come and gone, institutional knowledge has been lost, and the domain has changed. Our existing system for sending messages relies on a Redis-backed job processing library called Virk in the Elixir ecosystem. Unfortunately, Virk is now unmaintained and lacks good observability. One option we talked about was forking Virk and maintaining it ourselves. But Virk has some other issues as well, and the biggest one for our domain is that there's no built-in way to rate limit messages. And finally, our current system shoved all the existing logic to send a message into one Virk worker. We loaded all the data, we checked all the rate limits in one job, and if a message was rate limited, it was difficult to know why it was rate limited. And when we attempted to send the message again, we had to do all the work over again. We had to load all the message from our database and check all of those rate limits yet again. To better understand what finally pushed our system to its breaking point, we first need to go over a little bit of domain terminology. First, we send text messages, and we do that through providers. We don't talk directly to carriers. Instead, providers are the services that we use to send our text messages through. Everybody here has probably heard of Twilio, but there's a bunch of other ones out there too, and we use multiple of them. Carriers are mobile network operators like AT&T, Verizon, T-Mobile, or US Cellular. In the US, as far as physical infrastructure goes, those are basically it. There are many virtual network providers, but those all operate on top of physical infrastructure from these four companies. And most importantly for later, when we send a text message, we need to know which underlying carrier it is. When you send text messages on your phone to somebody, that is person-to-person texting, P2P. And strictly speaking, what we do at GetThru is A2P texting, application to person. So even though our customers may end up having a conversation with the people they're texting, it's still considered A2P because it's not coming from your phone, it's coming from our application. When sending those A2P messages in the US, they get sent through something called a 10DLC, a 10-digit long code. And basically, the carrier says that you can use this 10-digit phone number for A2P text messaging subject to some limits that they set. And those 10 DLC rules are administered by something called the Campaign Registry, TCR. Our old system had issues, but this is what really broke it. TCR is an attempt at the industry to self-regulate, the carrier industry to self-regulate to prevent federal regulation on A2P texting. They verify brands and campaigns prior to them being allowed to send A2P messages, and it requires brands to submit information about themselves, their use case, to provide traceability about the who and what of why they're going to be sending these text messages. So for example, if somebody's running in a local election and they want to send out a get out the vote text campaign, they have to have first registered their brand with TCR with a political use case, and the quality of information they submit will be part of determining if they're approved and how many messages the carriers say they are allowed to send. TCR was announced in 2021 and went into effect in 2022, and our current system has been struggling to deal with this ever since. So in 2023, we decided that continuing to build on the old system was not sustainable. We needed to start fresh. One of the first things we did was write an ADR, an architectural decision record. That document outlined the issues with the existing system, requirements for the new system, and a proposal for the architecture of that new system. First, we really needed to lessen the load on our database. The existing system was putting a very heavy load on it. The way it had to check everything again on every retry, no matter what caused that retry, was really hammering it. And plus, every message was being inserted independently, which was a lot of independent writes. We have a monolith architecture at GetThru, and we really like having that monolith, and if we want to keep it, we need to lessen the load on our database. We also wanted a separation of concerns between rate limiting and business logic. The way we had bolted TCR rate limits onto our legacy system interleaved the two and made it really hard to reason about what was going on. We also needed to respect all of the TCR and provider rate limits. TCR rate limits had been bolted onto the legacy system, and they just didn't work well. Also related to that was intelligent retries. The legacy system made it hard to know why a message was being rate limited. Since everything was checked in just one job, it was hard to tell at what point the message got rejected. Observability was a must. This is a pretty large and squishy requirement, but just about anything was going to be an improvement over our existing system. We needed to be able to answer detailed questions about the system's behavior and also be able to tweak that behavior at runtime without bringing the application down. We're big fans of open telemetry, but we would have needed to fork Verk to hook that telemetry in. One of the driving business use cases was batch sending. This is being able to send out a bunch of messages all at once without user intervention for each one. So for example, a university wants to send out their fundraising message at 9 in the morning. The initial message is the same for everybody. And so there's no need for somebody to sit there and click a button for every single one. It would be way better if we could just send all of those into the system at once. And then related to that is scheduled send, just the ability to schedule messages to go out at a certain time. And beyond all of that was the opportunity to rebuild a core part of our system from scratch. We had lost institutional knowledge about the old system. There were legitimate business and technical reasons to build this new system, but regaining that institutional knowledge with the current team was very appealing as well. Let's talk about our tech stack. It's different than possibly anybody else's in this room. As I mentioned, we're a 100% Elixir shop. So obviously we're going to continue to use Elixir here. Its emphasis on concurrency also happens to be really well suited to this problem space. Is there any other Elixir devs in this room? Oh, that is more hands than I was expecting. That's fantastic. But if you don't worry. I'm not going to show any Elixir code today. We're just going to talk about architecture. We had a couple of existing options in our infrastructure for enqueuing jobs. First, we have Oben. Oben is the go-to job processing library in the Elixir ecosystem, kind of won out over Verk. The problem for us is that it's tied to Postgres. We use Postgres. We love Postgres. But one of our goals is to reduce the load on our database. And if our job processing system is adding even more load to our database, that's going to cause issues. And that led us to Broadway. Broadway is designed for building concurrent and multi-stage data ingestion and data processing pipelines in Elixir. And importantly for us, it has fantastic built-in support for rate limiting. Broadway supports many different producers, which is what it calls the adapters to connect to something like Kafka or RabbitMQ, and a few others out of the box. We already had Rabbit in our existing infrastructure, so that made it an easy choice for us. It also has the niche advantage of Rabbit is written in Erlang, which runs on the same VM as Elixir, so we're pretty comfortable with debugging the internals if we need to. And because we already had Rabbit in our system, we didn't seriously evaluate any alternatives like Kafka. They're very similar tools. There's a lot of overlap in what they do, but we weren't interested in adding any more infrastructure to our system. We also already had Redis in our infrastructure. Redis is a bit controversial in the Elixir ecosystem. The VM gives you a lot of the things Redis does out of the box, but we have some particular use cases where we want persistent stuff in Redis, and that makes it a good choice for us. And finally, our backend is Elixir, and through the power of Phoenix Live View, our front end is as well. If you're familiar with Hotwire in the Rails world, or I think there was a Blazor talk right before that, Blazor in the C# world. Live View is the Elixir version. It's kind of the original inventor of this paradigm that's coming to lots of different frameworks at this point. Because of that, we write almost no JavaScript in our application. When I say 100% Elixir, that is almost 100% Elixir. And all of that comes into a project that we codenamed Super Collider. And I will say, I used to hate project code names. They're really annoying, but AI image generation has made them really fun, even though I can't spell. So this is it. I think we've checked off all of our requirements here. We can ship it. Does anybody have questions? I think maybe I'm seeing some stares in the audience. We should go over it a little bit. So a huge chunk of that diagram relies on a basic understanding of RabbitMQ. So we're just going to do a very high-level overview of how Rabbit works. This diagram is just a conceptual overview of Rabbit. First, the Rabbit server itself is a broker. So a producer is part of your application code that produces messages to send to RabbitMQ, and those messages get sent to an exchange. The exchange is responsible for routing those messages to queues, and most importantly, the outside world doesn't ever talk to a queue when you're sending messages in. You talk to the exchange, and it's the exchange's responsibility to figure out where those messages should go. And it knows how to route those messages based on the type of exchange and the bindings that you've defined. And a binding just defines how that exchange should route incoming messages. Our message bodies are JSON, but Rabbit is happy to use protobuf, message pack, CSV, whatever your heart desires. Rabbit doesn't care what the contents of your message bodies are. For us, we like being able to peek into our queues for debugging, so we went with JSON so it's still human readable. And finally, your application then creates consumers. Consumers connect to RabbitMQ and consume messages from a queue. And importantly, consumers can also be producers. And as we'll see in our pipeline, almost all of our consumers are also producers. For the rest of this talk, I'm going to shortcut things. But we're going to talk about sending messages to queues. Just remember, that's not actually how Rabbit works. But we're not doing any complicated routing rules internally, so it should be fine. Rabbit is also extremely configurable. We leaned into resiliency at the expense of scalability for now by making our queues persistent to disk and highly available across our cluster. In our case, losing messages is not acceptable. Your use case may be different. Maybe it's OK to lose messages. In those cases, there's things you can tweak to get more speed out of Rabbit at the expense of resiliency. But this talk is meant to be a case study of a system using RabbitMQ, not a deep dive into Rabbit itself. So let's move on to our pipeline. Our pipeline starts when a user clicks a button to send a message. We want to make sure that message gets into our database up front. Our legacy system did this too, but it did it immediately for every single message. User clicked the button to send a message, and we immediately persisted that to the database. And then only after that did we enqueue a work job. One of our goals in the new system was to lessen the load in our database, and this was a prime opportunity to do that. Hence, bulk ingest. Instead of persisting each message individually, we're going to persist them in batches with bulk insert operations. This is going to lessen the number of round trips to the database. We're still going to insert the same raw number of records, but we're going to batch them all together into more efficient transactions. In this diagram, we can see that a user clicks the button to send a message. This enqueues a message in our bulk ingest queue. And from there, we have configured a Broadway consumer to consume messages from the queue in batches. The consumer then processes all the messages in that batch at once, and bulk persists the database changes in as few round trips as possible. This includes persisting the new message, updating the status of the conversation, and some other miscellaneous metadata that we have to keep here for bookkeeping. And after all of that data is persisted, each message is sent along to the queue for the correct campaign, which we'll go over what that is soon. Broadway allows you to configure both the size and timeout of a batch. So if enough messages come in to fill the batch, we've sent out that many messages. But for example, if only 50 messages come in and we have a timeout of 100 milliseconds, if there are only 25 messages after those 100 milliseconds, we're going to send out those 25 messages. Getting the proper batch size has been more art than science so far, and it's something we're going to have to tweak going forward. And that brings us to our first lesson learned. One mistake we made in our initial implementation was to tie our message payload structure to our database schema. And this had a couple issues. First, it just tightly coupled them together. Any changes to our database schema risk changing the shape of messages in our pipeline. And there's a lot of messages in flight, and that can cause issues. Second, it increased the size of our payload. We were passing around a bunch of data that we needed in our database, but was not directly relevant to passing through the pipeline for sending messages. Now, luckily, we were able to fix this. Making this kind of fix is way easier before going live, and luckily, we were able to do that. It would have been way harder to make this kind of fundamental change after we were in production. We would have needed to support both message structures for some period of time until all messages had flowed through the system. Now, proper versioning of changes of even this pipeline struct does mean we have to handle that in the future, but being able to make those changes independently of our database structure is a big win. And bulk ingest is the point where this transformation happens. So messages get sent to the bulk ingest stage as our database schema. They get persisted to the database, and then they get transformed into the pipeline message for the rest of the pipeline. So this partially checks off our first requirement. We'll see at the end of the pipeline that we do some similar batching for updates after the message was sent out, but I'm going to go ahead and cross this off partially for now, and we'll come back to it. I'm not going to check this one off yet, but it also gets us a long way towards batch sending. Currently, all of our messages come from a user clicking a button in our system, but that doesn't have to be true. We could easily just batch send messages into bulk ingest now, and they would be efficiently processed. And this is a big point for doing as little work up front as possible when the user clicks the button. The first stage of our pipeline doesn't have to care, and it makes it easier to find other ways to send messages in the future. Let's move on to the campaign stage in our pipeline. So next, our customers send messages as part of what we call campaigns in our domain. A user creates a campaign, adds a list of contacts to it, and when that is launched, we attach a phone number from one of our providers that's going to be used to send all of the text messages. And all messages from a campaign are sent through just one provider. And it looks roughly like this. We saw the top of this diagram before. The bulk ingest consumer has a batch of messages, and once it's persisted those text messages to the database, it's going to produce new rabbit messages that will be routed to the appropriate queue for the GetThru campaign. Note that each bulk ingest consumer is also a producer. That is common throughout our pipeline. Each consumer consumes messages from Rabbit and then produces a new message to send to the next stage of the pipeline. In the case of bulk ingest, each batch is sending out multiple messages depending on the campaigns. So each campaign gets its own queue and consumer. When a campaign is launched, we dynamically create this queue and this consumer. In addition to the GetThru campaign queue, we're also going to, like I mentioned, dynamically start our Broadway consumer process. And this is going to start consuming messages from the corresponding GetThru campaign queue. Most of our pipeline stages are very simple. This campaign stage exists purely to check if the campaign is in the US. Because if it is in the US, it's subject to the campaign registry, TCR. So we need to make sure that our TCR campaign is properly configured, and then we can start sending messages. If the campaign's not in the US, we can just go directly and send a text message. We can skip this whole TCR part. And importantly, our customers can have multiple GetThru campaigns at one time, but often those campaigns are subject to the same TCR campaign. So for example, both campaigns 2 and 3 could be subject to TCR, and both of them use the same TCR campaign too. Let's go down the simple path for non-US campaigns first. These aren't subject to TCR, so we can just push our messages directly to our send message stage. And this is where we make an API call to our providers to actually send a text message. All these campaigns are non-US, so the consumers are publishing their messages directly to the provider queue for the campaign. There are separate queues for both SMS and MMS messages for each provider, and this is because each provider has a separate rate limit for SMS and MMS messages. So for example, provider 1 may allow you to send 500 SMS messages per minute, but they're only going to let you send 250 MMS messages per minute. Assuming a consumer can successfully send an SMS or MMS to the provider, we then publish 2 Rabbit messages. One's going to go to the bulk update queue, and another one's going to go to a side effects queue. And importantly, just because a provider has accepted our API request to send message makes no guarantees that it's actually going to be delivered to somebody's phone. They have just acknowledged that, yes, you want to send this text message. If we want to get the results of that, we have to wait for them to call a webhook in our system to handle that. Now, I mentioned provider rate limits. Each provider limits how many SMS and MMS messages we can send in a window. So remember that one of our requirements was to have a clean separation of concerns between this rate limiting and our business logic. And the way we do that is through back pressure. Back pressure is the concept of a consumer telling a producer or a source of events how many at once at a time. Rabbit itself has no concept of rate limiting or back pressure. Instead, we configure this through Broadway. Let's walk through some examples. So let's say our provider is rate limiting us at 100 SMS messages per second. We have a consumer that's going to make an API call to the provider to actually send the SMS. And we configure that consumer to demand 100 messages per second from a Rabbit queue. In this case, we demand 100 messages, and we can see that our queue conveniently has exactly 100 messages. 1 second later, the consumer is going to demand another 100. There's nothing in the queue, so 0 actually gets supplied. But what if there weren't enough messages in the queue to satisfy our demand to begin with? In this case, we're again demanding 100, but the queue only has 50. Those 50 get supplied to the consumer immediately. But what if another 50 messages come in then? Rabbit is going to push those 50 messages to the consumer to satisfy the outstanding demand. And finally, what if there are too many messages in our queues? In this example, the queue has 150 messages, but our rate limit is still 100 per second. The consumer demands 100 and is immediately supplied with 100. The consumer processes all those, demands another 100 in the next second. There's only 50 this time, so we're back in the same situation that we were before. These examples all show one consumer with one processor, but you could configure to use multiple processors per consumer as well. So maybe you have so many messages coming in and the processing requirements per message are so high that your one processor can't keep up. So you spin up multiple processors to handle those in parallel. And this kind of concurrency is really Elixir's bread and butter, and Broadway makes it really simple to use. There's a lot more you can do with Broadway, but this is a reasonable enough explanation of back pressure for our purposes. Our consumers are all configured to use one processor with a rate limit equal to the provider's rate limit for the message type. So if our provider has set a rate limit of 250 MMS per second, we configure our rate limit in Broadway to do the same. And then back pressure is going to ensure that we never exceed our rate limit with the provider. So messages may pile up in Rabbit though, but that's an entirely different problem. That is, we have too many messages coming in to send out through our providers, and that's something we need to talk to our providers about. So that checks off another one of our requirements, our separation of concerns. We rate limit API calls purely through configuration. When the consumer processes messages, it can focus entirely on the business logic. That doesn't mean things still can't go wrong, though. We still need to be able to retry messages. The provider could be down, there could be bugs in our code. Depending on the scenario, we might want to retry. And a good retry scenario is trickier than you would think in Rabbit. There are 3 simple ways to handle failure in Rabbit. You could discard the message, you could requeue it, or you could send it to what's called a dead letter exchange. Discarding messages is not acceptable in our system. If we discarded messages, that text message would never get sent out and our customers would not be happy. Requeuing is also a non-starter. If our provider is down, just requeuing the message to send it again right away when it comes back to the front of the queue is just going to spam the provider even though their system is down, and they're probably not going to appreciate that. So that one's out too. And in fact, this exact problem is one of the issues with our legacy system. We've had situations where we spam retries, and it's a pretty helpless feeling to know exactly what the problem is in production, and you can't do anything about it at the time. So that leaves us with dead lettering. Initially, it seems promising. It's a nice fallback, but requires knowing what to do with those failed messages then. And if you have one corresponding dead letter queue for every queue in your application, it can be difficult to automatically recover. You end up having to manually shovel messages from your dead letter queue back to the working queue. But what if we tried to set up a retry exchange with a per message time to live, a TTL, and a dead letter exchange of the worker queue? So when the message fails, we'll increment the number of times that particular message has failed to get an exponential backoff. Then we'll set that as the time to live of the message in the retry queue. And when the first message in it reaches its TTL, we'll move it back to the worker queue for retry through the exchange. That sounds great, but it has a fatal flaw. Rabbit won't expire messages until they reach the front of the queue. So let's look at this example. Here we have a retry queue that contains 3 messages. Our first message in the queue has a TTL of 8,000 milliseconds, the second one 3,000, and the last one 1,000. At 1,000 milliseconds, the last message in our queue is at its TTL, but Rabbit can't expire it. It's not at the front of the queue and the front message isn't expired yet. At 3,000 milliseconds, our second message expired, but we still can't do anything with it. It's stuck. Finally, at 8,000 milliseconds, the message at the front of our queue has expired. Message will be sent back to the exchange, then message 2 will come to the front, then message 1. Those are already expired, so they go out right away. But every message in our queue effectively had a time to live of 8,000 milliseconds because that was the TTL of the first message in the queue. The way we worked around this is to set up retry queues per TTL. So all messages on their first retry would get sent to queue.1000. All messages on their second retry to queue.2000, and so on as the backoff increases. If every message in the queue has the same time to live, then they will expire in order, and no messages will have a shorter TTL and get blocked by one in front. Does anybody see a downside to this, though? Go ahead. Correct, yeah. So you can't, if you're familiar with the term jitter, when you're exponential backoff, you often want to include jitter to smear those retries across a time so it's not a thundering herd of everything retry at the same time. We unfortunately can't do that with this system, but we consider that an acceptable trade-off to get predictable retries in our system, and we're just going to rely on Broadway back pressure to avoid that thundering herd problem as they come back out. So this is one of the most important things you could take away from this talk. If you're building an event or message-driven system with a lot of retries, read this article. It's by Brian Storty. It's a good chance that it's going to spur a lot of excellent discussion with your team about your architecture and your domain. And even if this particular solution doesn't work for you, you're probably going to end up in a better place for having read it. So this retry queue setup solved a lot of problems for us, but it didn't come without any complications. Besides the limitations of jitter on our backoff, there's also a lot of dynamic queue creation going on. This will become obvious as we continue to build up the pipeline for our domain, but we're going to end up with a lot of queues in this system. And almost all of these support retries, which means that the potential for a lot of retry queues. So we still need to figure out over time how many retries make sense for various stages in our pipeline and what that backoff schedule should actually be. And that's just going to take iteration over time in production. So that checks off a couple more requirements. We're now respecting all provider rate limits, and we have some intelligent retries. So we've made our API call to provider to send a text message, but we still need to update our database to reflect that that message has been sent. Bulk ingest helped with write performance when ingesting messages into our system. Creating a pipeline message struct to pass through the pipeline itself helped with read performance. We don't have to hit the database as much. We know exactly what we need. There was still one big win we wanted, though. We wanted to be able to bulk update messages at the end of the pipeline as well. To do that, we added a bulk update stage. It uses the same kind of batching we use for bulk ingest, with just a couple of different wrinkles. First, we need to update the database whether we actually sent a text message or not. In some circumstances, we need to update the message status to failed. Sometimes a message we know is never going to send, we never actually sent the API call to the provider. Maybe it's been too long. Maybe the client actually closed their campaign while the message was going through our pipeline. We don't want to send those out. There's some other reasons as well, but we need to persist those messages with this particular status. Second, we need to broadcast that this message has been sent and its status updated in the database. So maybe the UI needs to update in some way. Maybe some other system cares. In many other ecosystems, this would be a job for the message broker again. But that's not necessary in Elixir. Elixir systems are made up of tiny processes that are considered actors. And in the actor model, actors just send messages to each other. Using Phoenix's pub/sub support, we can easily publish messages to other actors in our system, so that systems can subscribe to it. No extra messages are needed. So in our case, our live views are often subscribing to changes that are happening on our back end, and we get it. And this works across network boundaries as well. One node in our cluster could be processing bulk messages for bulk update. Another node in our cluster could be handling a live view for our user. And they can be notified transparently. And we get all of this pretty much for free because of the VM the Elixir runs on the Beam. And getting this kind of power with such little effort feels like magic. Elixir often feels like it's just forbidden alchemy in this way. So earlier, we partially checked off lessening the load on our database, the combination of bulk inserts, bulk updates, some usage of message caches throughout the pipeline. That's really lightened the load on our database. So I'm comfortable crossing this one off fully now. Like most systems, there are side effects we want to happen when a message is sent. The pub/sub and bulk update is certainly a side effect, but I'm talking about external side effects here. For example, our clients might want to update a third-party system just to say that they had contacted a voter. To accommodate this, we added one more stage to our pipeline for side effects. Details depend on the nature of the integration, but the general idea is outlined here. So now our provider consumer has published two messages. It published to the bulk update queue, but it's also publishing to an outgoing side effects queue for the integration. Messages are consumed from the side effect queue by side effects consumer, just as we've seen, and processed. Right now, we just have one queue and one consumer to process all side effects, but we'd like to split this out into separate queues for each third-party integration. This is for both resiliency. We shouldn't have, if one third-party integration there down, it shouldn't be blocking other ones, and it would allow us to apply separate rate limits if necessary for those integrations as well. So that does it for our non-US customers. We can see that their GetThru campaign is outside the US. We send the text message through a provider while respecting that provider's rate limits. We update our database and we handle side effects. But what about this big middle part of the diagram? This is where the campaign registry and carrier rate limits live. And we're going to make gratuitous use of tacky PowerPoint animations. So remember that TCR is the carrier industry's attempt at self-regulation of text messages. They want to allow as many of these A2P text messages as possible through for various use cases, but they want to keep them from annoying so many people that the federal government steps in and regulates them. In practice, what this means is that we register a TCR campaign on behalf of our customers. TCR takes a whole bunch of information about the campaign and about the customer and spits back what they call a vetting score. And this vetting score determines how many SMS and MMS messages can be sent in a given interval per carrier. So that brings us back to this scary looking part of the diagram. Starting at the top with our campaign consumers, let's just assume that this campaign is in the US, which means it's subject to TCR. So we send a message to the TCR campaign for that GetThru campaign. TCR has given us rate limits per carrier, so next the message gets sent to the appropriate carrier queue for that TCR campaign. This is still a lot though, so let's just look at what happens for one carrier, AT&T. So we start with our campaign consumer again, which determines that the campaign is in the US. It gets passed to a TCR campaign queue, and the consumer for that queue looks at the carrier text message recipient, the carrier for the text message recipient, and the type of message that we're using to forward it to the correct carrier queue for that campaign. So for an SMS message to an AT&T phone number, we're going to end up at this TCR campaign one AT&T SMS consumer. This consumer is going to pull messages from the queue while respecting that carrier rate limit we got from TCR. Once again, we're going to do this with back pressure. So if AT&T says that we can send 100 SMS messages per minute, we're going to configure Broadway for this consumer to pull 100 messages per minute at most. This consumer exists purely to rate limit messages. It has no other reason to exist. It's so that we don't get in trouble with TCR. It just rate limits and forwards messages on to the correct provider queue. Now, you might be asking what the point of this TCR campaign queue and consumer are, and that's a very good question. It shouldn't exist, and we're going to remove them. You should not add stages to your pipeline as a way of separating business logic or business concerns. They should only exist to control concurrency and or back pressure separately for that stage. The TCR campaign had been low-key bothering me, but while preparing this talk is when I really realized it had no reason to exist at all. And this kind of separation is even called out as an anti-pattern in the Broadway documentation. But of course, not every carrier can do everything the same way. What fun would that be if our domain didn't have some more complexity? Let's talk about T-Mobile. T-Mobile has decided that their TCR caps are per day, and they don't care if it's SMS or MMS. No big deal, right? We could just use back pressure with a really long window. That'll work fine. But not quite. The issue is that deployments would bring down our app and reset the rate limit for the day, which isn't acceptable. We need that rate limit to be respected for the entire day, no matter how many deployments we're doing, no matter how many nodes are coming up and down in our cluster. It's not a big deal if we have a per minute or per second rate limit and we do a deployment and everything's going to be fine in the next second or minute. But if the window is an entire day, using Broadway back pressure is not an acceptable solution. So this shows our TCR campaign and consumers for T-Mobile. Instead of using Broadway back pressure, we instead rely on persistent counters and Redis. And T-Mobile has one more curveball for us as well. They don't want a rate limit by TCR campaign. If you have one company that has multiple TCR campaigns, they want to rate limit by the employer identification number. So I don't know, somebody's not gaming this system. So we keep track of how many messages have been sent for that brand's EIN for that day in Redis. Every node in our cluster checks that same key in Redis for that brand's EIN. So if we haven't hit the limit yet, the message can be forwarded to the correct provider queue. If we have hit the limit, then it needs to be sent to a retry queue. We talked about retries in the context of providers, but the same retry strategy applies to all of those carrier consumers as well. Which brings us to another lesson learned. We're pretty happy with our dynamic retry queue strategy, but it isn't appropriate in all use cases. T-Mobile is one of those. When we hit the daily cap for T-Mobile, we know exactly when we can send that message out again. It's the next day. So we don't actually need to be doing these dynamic retries here. We don't need to try it again in a second or 2 seconds or 4 seconds or 8 as the back off goes up. We know with 100% confidence that all those retries are going to fail and we should be sending them out the next day. The good news is we actually fixed this the other day. I just didn't update my slides. We calculate the TTL of the message for a time after we've closed the campaign for the day. So when the campaign comes back up tomorrow, it's just going to see those messages in its queue to start. We don't have to do all these retries. So now we've satisfied a requirement to respect all of our TCR rate limits as well. Now you may have noticed this is potentially a lot of queues and a lot of consumers. For each TCR campaign, there are 4 carriers. They have both SMS, MMS, and MMS, so we get 8 queues per TCR campaign. But then you double that because we also have dead letter queues for each one of them. And then there are potentially even more because we have these retry queues that can be created dynamically as well. And this brought up the question of resource usage. How much memory were all these queues and consumers actually going to use? And were we reasonably confident that we were going to be fine? We thought we were going to be, but we needed to do some benchmarking to be sure. The good news is that we were right, but it's still important that we checked. An empty rabbit queue only uses about 20 kilobytes of memory, so we weren't paying a large penalty for having all of these empty queues sitting around if there's no traffic going through them. And the same is true for Broadway consumers. Processes are cheap on the beam, so even though a Broadway consumer sets up a supervision tree with multiple processes running underneath it, those processes don't use a lot of memory. But don't assume this is true. Validate that assumption for your domain. So that is the entire pipeline from beginning to end. That's not all we had to build, though. The pipeline is the core of the super collider, but not all of it. There are some other restrictions beyond rate limits that we had to worry about. The main one is sending windows. So hopefully you're not getting campaign text messages outside of the legally allowed hours. If you are, they're not coming from us. But regulation prohibits phone or text solicitation outside the hours of 8 a.m. to 9 p.m. On top of that, our system has an additional restriction on when initial messages can be sent. So for example, a campaign may have a timely fundraising message that they want to send out for a university's giving day. If they don't get through all of those messages on the giving day, sending them out tomorrow, they don't want those to go out. The message explicitly refers to giving day is today. It would be weird to start getting that text message tomorrow. And the way we enforce this is by dynamically creating parts of our topology when a campaign opens and tearing it back down when a campaign closes for the day. And to do this, we lean hard into what Elixir does best, which is small independent processes organized in what they call a supervision tree. The bare minimum you need to understand is that Elixir applications can be thought of as a tree of processes, and all the non-leaf nodes here are supervisors. This is a simplified supervision tree for our application. When the application starts up, we create a campaign worker process for every GetThru campaign in our system, and each campaign worker process is responsible for calling the dynamic topology supervisor when the campaign opens to create that GetThru campaign consumer and the TCR campaign consumer, if one doesn't exist yet. And then the campaign worker process schedules a message to itself when the campaign is ready to close. Let's look at an example of this. So let's say we've started our application up at 7 a.m. and the campaign 1 is scheduled to start at 8 a.m. No consumers have been started up for this campaign yet. So if any messages get sent through admins or something else, those messages are just going to sit at the campaign queues. And we're not actually going to send any text messages to people yet. And this is what we want, because we shouldn't be sending any messages out until 8 a.m. when this campaign opens. So campaign 1 schedules a message for itself at 8 a.m. to start. 8 a.m. rolls around, and that message gets delivered to the campaign worker process. This starts all the consumers for that campaign. The GetThru campaign consumer has been started, the TCR campaign consumer has been started, and all those TCR campaign carrier consumers have been started as well. And once those are started, the campaign worker schedules another message for itself, this time for 9 p.m. to close. Now 9 p.m. rolls around, the close message is delivered to the campaign worker, and it shuts down all the consumers. All those queues can still exist out there, but there's nothing consuming messages from them, so we're not going to be sending anything out when we shouldn't be. An earlier iteration of this campaign worker process tried to be more dynamic than necessary and not start up the consumers until they were actually needed, like when a message was actually tried to go through the pipeline. So for example, if a campaign opened at 8 a.m., no messages were sent until 8:30 a.m., we wouldn't start the consumer until 8:30 a.m. when that first message came up. And we did this by having each campaign worker process poll. Unfortunately, we had some bugs, though, and that caused a severe performance regression in other parts of our system. We are being more dynamic than we needed to be here. Moving to our current system of only scheduling messages for open and close times made the system easier to understand and less bug-prone. The lesson here is, like, for us, Elixir processes are cheap, and we had over-engineered part of our system, and we paid a price for it with issues in production. We talked a lot about rate limits, but we've been ignoring an important caveat about them. Our app runs in a cluster with multiple nodes. Each node is going to have consumers taking messages from each queue, but the queues and the rate limits are global. Our providers don't care how many nodes we have in our system. They care that we are respecting their rate limit that they have set for us. This means that we have a rate limit of, say, 300 messages per minute, and we have 3 nodes in our cluster. Then each consumer needs to be rate limited to 100 messages per minute on each node. So overall, we're still respecting that provider's rate limit of 300 messages per minute, and we're spreading the load evenly throughout our cluster. But what happens when our cluster resizes? Luckily, the Beam VM that Elixir runs on has us covered again. We can subscribe to events that let us know when a node has joined or left a cluster. And we have a rate limit monitor process on each node that can subscribe to these events. A node leaves or joins the cluster, we can update the rate limits on our Broadway consumers at runtime. Another way this can happen is if TCR changes the score for a TCR campaign. This will happen if we have one of our customers submit information in the hope of getting a better score for them. They'll update us via webhook that the score has changed, and we can, once again, at runtime, dynamically update the rate limits in our Broadway processes. One of our other requirements was observability. We've tackled this from a couple of different directions. First, we're big fans of open telemetry. We use this to track a lot of information, traces going through our system, metrics around retries, failures, successfully sent messages, and these give us a high-level overview of how the system is behaving. Beyond that, we've also been building an internal campaign dashboard for staff members to track the health of the system. If issues come up, we can see that a campaign is unhealthy and pause it while we triage the issue. This will tear down all the consumers, just like if the campaign had passed its sending window for the day, so nothing's going to go out. This dashboard also lets us see at a glance all the rate limits being applied to a campaign. We also segment our customers by release groups, and this dashboard lets us easily turn the super collider on or off for various groups of customers. So we can go back to our legacy system for some groups of customers, super collider for some groups of customers for a slow rollout as necessary. And we had to do it this way because our feature flag library doesn't have support for side effects. So since we want to be spinning up and spinning down all this topology stuff dynamically, we had to build this part ourselves. This dashboard has a lot of potential, but it's also pretty immature right now. We haven't hit the pain points that we know that we're inevitably going to hit in production. And once we hit those, we'll have a better idea of what data to surface and what control points we need to manipulate the system at runtime. Even at this point, though, it's considerably better than anything we had in our legacy system, where we had no ability to shut off parts of the system when it was misbehaving. Debugging issues in production was a fraud experience. In Elixir, you can actually just shell into the running system and manipulate it at runtime, and we had to resort to that a few times. So I'm going to check off observability here, but we know that we have a ways to go. The bones are solid, but we need more experience with the system to know what gaps to fill. We did small testing throughout the build-up to release, but as we were getting closer, it was decided we needed a more thorough QA plan. It was time to put the super collider through its paces. It didn't go well. So what happened? What did we miss? Beyond the normal bugs when implementing a new system, there were a couple of large issues that we missed that we needed to address. The first was UI related. Throughout development, we were seeing a number of oddities in the behavior of our UI while developing the pipeline. We kept putting them off, though. We thought they certainly couldn't be a big deal. I mean, the super collider was completely decoupled from the UI, right? There's no way these UI issues were caused by our new messaging pipeline. There's just no way. It's not possible. Except it was. We were very wrong. The existing message sending UI didn't handle the new pipeline well because it made a lot of implicit assumptions about the latency of data being inserted into our database that the super collider broke. In addition, the messenger live views, where people actually send out text messages, are by far the most complicated UI in our app and had accumulated the most tech debt. It reached the point that updating the existing messenger live views just wasn't worth it. Our legacy system needed to continue to work while we rolled out the super collider, and the pain of continuing to support these two backends with one UI wasn't sustainable. So we declared tech debt bankruptcy and forked our messenger to a new version that only worked with the super collider. What we had thought would just be some quick bug fixes, and then thought would be just some changes that broke backwards compatibility, ended up turning into a full rewrite of the core logic of these UIs. In the long term, this is a good thing. We were able to drastically reduce the database load from our UI even more. We used to hit the database constantly to load new data. Now we're optimistically updating the UI when sending messages, and we saw the pub sub stuff in bulk update before. Now we just pub sub to our UI to keep things consistent. And we do all of this with very little traffic to our database. So we ended up in a better place, but it was pain that we didn't plan for. In the short term, though, it was disastrous. It significantly delayed our launch. So don't assume that parts of your system are decoupled. Pay attention to those bugs that are creeping in that you can't explain. They may be pointing to a deeper issue. We ran into one other large issue as well. This entire talk, I've been talking about rate limiting by message, but that's been a little white lie. SMS messages are comprised of what's called segments. And when a message gets to a certain length, the message gets split into multiple segments. And it turns out that our SMS rate limits are also by segment, not message. In our defense, a lot of the documentation from TCR and the providers is unclear about this, but it doesn't matter how we got there. Our rate limiting was wrong. We thought about hacking around it by looking at the average segments on a message, which would stem the bleeding until we can get a real fix. But unfortunately, there's a wide distribution in the number of segments on our messages, and we were going to exceed our rate limits too often to be comfortable with. What we really wanted was a weight on a message so we could say how much it counts towards a rate limit. So if a message is 3 segments, we want it to count as 3 towards the rate limit, and then we can continue to rate limit through back pressure. Unfortunately, this is not supported out of the box in Broadway. Fortunately, though, Broadway is open source, so we forked it internally to add weights to messages. So for now, we're maintaining this fork ourselves, but we're hoping to get it upstreamed back into Broadway one day. We think the main issue is going to be philosophical. Does the Broadway team want to have weights on messages? Is there a reason they haven't added it? We ran into lots of weird corner cases, and you can get yourself into some bad spots with configuration when we were implementing it. We haven't had those conversations with the team yet. Which brings us to another rough lesson we learned. Understand your domain. We didn't ask enough questions to understand earlier that many of our rate limits were by segment and not by message. This was wrong in our old system, and it was wrong in our new system until we realized this, and we didn't question it. I think we would have ended up in a similar place of adding weights to messages in Broadway, but this was high-risk work, and you want to identify that high-risk work up front. You want to front-load it on your project, not tack it on to the end like we did. So be sure to poke and prod at your domain from different angles. Be ridiculous about it. Play devil's advocate. Consider doing pre-mortems on projects. Ask what would happen if X failed or if Y was true. You can come up with some ridiculous scenarios you don't care about, but at least you're consciously setting them aside to think about for later if you need to. So now we come to our moment of truth. We fixed these issues. We rewrote our live views for our Messenger UI. We forked Broadway so we could successfully and correctly rate limit by segments instead of messages. I submitted this talk to Stir Trek in late January, and that was when we were starting our UI testing. Has anybody here ever thought a project was almost ready to launch and then learned that there was a bunch more work to do? That you had done the first 80% and you only had the second 80% to do? That's why I have to stand before you and say we haven't actually shipped yet. We're hoping to ship very soon, hopefully for real this time. That's why I can't stand before you today with lots of pretty charts showing our performance and production between the two. That's what I was really hoping to show. And for that, I apologize. But I'm sure just about everybody in this room has been on projects in similar positions. You just didn't have to be up in front of everybody, admitting it publicly. So let's talk about what we liked. Writing an ADR was a great early first step. It was a touch point for the team to agree on what was being built and the high-level architecture. I actually joined the team after this project was started, and being able to refer to that ADR was very helpful in getting up to speed. It wasn't a panacea, though. We would have liked to have found out about our segment rate limits up front. That would have been something that would have been great to have in the initial ADR. There's lots of philosophies out there about what should go in an ADR. I suggest starting very light and adding more complexity as you need. Our new pipeline is much easier to unit test than the old system. Stages are completely isolated from each other, and we've structured our modules to make that core business logic testable without any dependencies on Broadway itself. XDoc is the documentation system in Elixir and has been fantastic for us. It generates very nice documentation from Markdown that lives right next to your code. We are able to generate documentation at multiple levels of understanding. You can embed mermaid diagrams right into it. I constantly referenced our own documentation when putting together this talk. The way we were able to rate limit messages in Broadway with back pressure was great. It's way better than our previous system of constantly retrying messages. It wasn't ideal that we had to fork Broadway to add weights to it, but even that was way easier than we expected. We've been very happy with Rabbit so far. Because we're an Elixir shop and Rabbit is written in Erlang, debugging issues for us hasn't been anywhere near as intimidating as it might be for other places. The lesson learned here is to use tools that you're already comfortable with. Don't introduce new infrastructure that you don't need. We already had Rabbit in production for other systems. No need to add anything else. And because we're doing less work up front and bulk inserting as the first stage in our pipeline, our UI became more responsive as well. A downside of this was that we broke our expectations on our UI. We ended up having to rewrite a bunch of that. But our UI performance is just way better than it was before. And finally, we continue to love Elixir. We have a small team of 6 people. Over the past 6 to 7 months of building this, only 1 to 2 people have been working on this at any one point in time. That's not a lot of engineering effort for such a complicated system. It's more than we thought it was going to be, but still less than I think it would be in a lot of other ecosystems. Future improvements beyond, actually shipping to production. We haven't implemented batch and scheduled sends yet, but with our current architecture, that should be pretty straightforward. We fixed this earlier in the week, but there is some other things we could still do with different retry strategies for different use cases. I mentioned before, we currently have 1 queue in consumer for all third-party integrations. We'd love to split those out into separate queues in consumers. We got a lot of tech debt to clean up because we are currently supporting 2 systems for sending messages in production. Everybody's looking forward to deprecating the old system so we can delete a ton of code. Those are the best PRs that you can ever submit. While our unit testing is much better, we struggled to write comprehensive automated tests for parts of the system because of our dependency on Rabbit. We would benefit a lot from starting to look at system-level tests of various scenarios of messages going through the entire pipeline. End-to-end load testing is currently very expensive for us because we send out actual text messages. And by expensive, I mean dollars. So we have the beginning of our own internal mock provider. Building this out more is necessary, though, because right now, any load test we do costs a lot of money. The bulk inserts and updates helped a lot with database performance, but there's still more caching we could do throughout the pipeline to eliminate even more hits on the database. We have a good start on observability, but we need to see more information in production. Our goal is to have it hardened and very observable in the lead up to the November election when we're anticipating the load on our system to be the highest. We're using OpenTelemetry, but the service we use for it only recently added support for linked traces. This would allow us to link together all the traces for a message as it flows through the system, which would make debugging certain scenarios much easier. And finally, pie in the sky ideas. RabbitMQ also supports streams. So if we had a stream per campaign in addition to these queues, we could do an event sourcing system where we could replay all messages for a campaign going through the system for debugging purposes. So overall, we're pretty happy with what we built. We recognize there's a lot of polish to be done over time, but we're confident that we have a system that can stand up under the load of an election season. I wish I was standing here with a system in production and hard data to show you, but unfortunately, things didn't work out that way. Many thanks to everybody I work with at GetThru. I'm not one up here talking, but everybody on our team worked on this project in various ways. If you have any questions, come on up and chat and find me later. One of my coworkers, Matt, is here as well. You can also track him down about it. He is probably more responsible for any single person at GetThru for building this system. The slides will be available on GitHub. You can find me on Mastodon or in the StirTrek Discord if you have any questions after the conference as well. So thank you. Enjoy your day. Any questions? Everything in our system is in UTC, but yeah, it's up to who's ever creating the campaign it's up to our customers to choose a window that is legal. Good.
Curious, given all the timing of messages going out and retries, is there an end-to-end strategy for testing
We're working on it. Yeah, that's like I mentioned at the end. We really need system level tests. Like we need to have a pipeline we can set up scenarios for testing and send messages through the entire thing. Good.
So within a queue, they're all going to the same endpoint. So why set a retry on each individual message? Why not set a retry on, say, one? And then as soon as it makes it, then you can start retrying all the others.
I'm not quite sure I understand.
So you said you're setting a TTL on each message.
Oh, I may have misspoke there.
Okay.
So the retry, the TTL is set on the queue itself.
Okay. Makes sense. Yep.
Yep, sorry.
Got it.
Oh,
What's your maximum throughput you can get?
TBD. We're interested to know that question as well, the answer to that as well. Toll-free numbers? Just 10-digit right now. All right, if there are any other questions, just come on up.